Okay, this is the problem we are going to discuss in this lesson. Draw the shear force and bending moment diagram for the following beam. Here you can see the beam is given. 8 meter length beam is simply supported beam. Here you can see the distributed load. The distributed load intensity is varying from 3 kN per meter to 6 kN per meter linearly. Okay, linearly varying distributed load. Then as a first step, I am going to do the freeboard diagram for the entire beam. Okay, let me do the freeboard diagram for the entire beam. Then support reaction RAY, RB. Here 3 kilonewton. Here. The distributed load is linearly varying. Here this value is equal to 6 kilonewton per meter. This value is equal to 3 kilonewton per meter. This N, AN, this N, BN. Okay, this is the freeboard diagram for the entire beam. Okay, first of all, I am going to find this one thing. Here is a pin supporter now. Let's take RAY, RAX also. First of all, I am going to find these support reactions. Okay, by resolving the forces in horizontal direction, RAX is equal to 0. Then by resolving the forces in vertical direction, RAY plus RB is equal to the load produced by this distributed load. The resultant of this distributed load, how we are finding the result of this distributed load, that is equal to the area of this trapezoid. Area of this trapezoid. So let's take let me mark this resultant force. The resultant force R. Here, the resultant force we can calculate 3 plus 6 divided by 2 into the distance between these two parallel lines, that is equal to 8 meters. 8. This value is equal to 36. Let's take this equation as equation 1. Then I am going to take the moment around this A point. Take the moment around this A point, RB into 8. Then the moment produced by these individual areas. Here this trapezoid I am going to divide into two areas. One is the rectangular section and the triangular section. Then I am going to consider this rectangular section separately and the triangular section separately. So what is the moment produced by this? Let's take this moment as R1. Sorry, force as R1 from this rectangular section, and for the triangular section, let's take it as R2. Okay, what is the moment produced by this load due to the rectangular section? That is equal to minus R1 into the distance. R1 is equal to the area. Area is equal to 3 into 8. The distance to this centroid of this area is equal to 4. Then moment produced by the force from this triangular section, that is also minus. The distance is equal to 2/3 from into 8. Then area of this triangular area is equal to half into distance. 8 into height is equal to 3, equal to 0. By simplifying this equation, you can calculate the RB. You can calculate the RB. For the RB, we are getting 20 kilonewton. RB, we are getting the 20 kilonewton. So then RAY is equal to 16 kilonewton. Okay. So in order to find the shear force equation and the bending moment equation, I am going to section this beam at the x distance. Somewhere here. X distance from the A. Okay, let me draw the free body diagram for the separated beam part. The x distance. And the distributed load. It is 3. The height is equal to 3. The length is equal to x. So let me mark the shear force. The bending moment. Okay. So length is equal to x. Then here RAY. So we have to mark the RAY is equal to 16. See the free body diagram for this separated beam part. Then this height, we can calculate this height. Here, this height varying for 8 meter length, the height is increased by 3. For x meter, 3 divided by 8 into x. So then this height is equal to 3 plus 3 divided by 8 into x. Okay. Then first of all, I am going to find the shear force. To find the shear force, I am going to resolve the forces in vertical direction. Here, shear force minus shear force plus 16. Then total force produced by this trapezoid area. The area we can calculate. That is equal to minus x divided by 2 into addition of 2 parallel sides. 3 plus 3 divided by 8 minus 8 into, that is equal to 0. By simplifying this equation, we can get the shear force equation. The shear force is equal to minus 3x square divided by 16 minus 3x plus 16. The shear force is equal to minus 0.1875 x square minus 3x plus 16. This is the shear force equation. Here you can see the shear force having the parabolic variation. This is the variation. Okay. Let me find the shear force at x is equal to 0 value. Shear force at x is equal to 0, that is equal to 16. Shear force at x is equal to 8. Value is equal to minus 20. Then I am going to find the symmetric axis of this parabola. The symmetric axis x is equal minus b divided by 2a is given the symmetric axis. Here minus 3 divided by 2 into a minus 0.1875 Here this value is equal to minus 8. So it is equal to minus 8. The x is equal to minus 8. This parabola having maximum. This parabola having the maximum. So this data we need when you are going to draw the shear force and bending moment diagram. It's the maximum value and the minimum value and boundary values. Okay, next I'm going to find the bending moment equation. To find the bending moment, I'm going to take the moment around this O point. By taking the moment around this O point, the bending moment, here it is 16 minus 16 into x. Then the moment produced by this distributed load. So I'm going to divide this distributed load into a rectangular section and the triangular section. For the rectangular section, let's take this resultant of this rectangular section, R1. For the triangular section, let's take it as R2. Then the moment produced by the rectangular section alone, that is equal to the clockwise, the plus the 3 into x divided by 2. Then the moment produced by the triangular section, that is also plus the area is equal to half into x into height, and the height is equal to 3 divided by 8 into x. Then this is the area. So then to this area the length is equal to 1/3 of x. So yeah, there is all the moment acting. So that is equal to 0. By simplifying this equation, we can get the bending moment equation. The bending moment equation is equal to minus 0.0625 x into q. Then minus 1.5 into x into c square plus 16x. Then bending moment at x is equal to 0. By substituting the x is equal to 0 in this equation, we are getting the 0. Bending moment at x is equal to 8. By substituting the 8 in this equation, again we are getting that is equal to 0. Here you can see the bending moment is having the cubic variation. So to find the maximum and minimum values, I am going to derivate this equation with respect to x. By derivating the bending moment equation with respect to x, we are getting the shear force equation. The shear force equation is equal to minus 0.1875 x square minus 3x plus 16. At the maximum and minimum, this one should equal to 0. So then I am going to find the root of this equation. So you can use your calculators to find these roots. So let me write the roots x1 and x2. Actually, the one root is negative. We no need that root. Yeah. So let me write the positive root. X is equal to 4.22 meters. This is the valid root for this problem. At x is equal to 2.2, the bending moment maxima is so minimized. To determine that is maximum or minimum, I am going to take the second derivative of this bending moment equation. The d2 bending moment dx square is equal to minus 2 into 0.1875 into x minus 3. Okay, here this is the expression we are getting. If you substitute the x is equal to 4.22, we are getting the negative value, always negative. So at this point we are having the maximum value. Okay, now we have obtained all the equations. Now we are ready to draw the shear force and bending moment diagram. Okay, let's see how to draw the shear force and bending moment diagram. Here I have summarized all the equations so far we obtained. This is the problem. This is the problem. The shear force equation is this is the shear force equation. The shear force at x is equal 0, value is equal to 16. Shear force at x is equal to 8, the minus 20. Shear force variation having the symmetric axis at x is equal minus 8. X is equal minus 8. Okay, the bending moment, this is the bending moment equation. The bending moment at x is equal 0, the value is equal 0. The bending moment at x is equal 8, value also equal 0. And the bending moment at x is equal 4.2 meters. The bending moment maximize. The maximum value is equal 36.88. By substituting this value in the bending moment equation, we can get the 36.11 kilonewton per meter. Sorry, kilonewton meter. This one should be a kilonewton meter. Okay, now we are ready to draw the equations. First, let's draw the shear force equation. Here, the shear force at x equal to 0. Let's take the 16. At x is equal 8. So value is equal to somewhere in here, the minus 20. Okay, let me draw the graph. This point 4.22 meter point. Okay, this is how we are doing this one as well. This is how the shear force is varying. This is how shear force is varying. So then how the bending moment is varying. Here it is 0, here also 0. At this point it is maximized. This is the maximum point. Let's take the 36.11. 36.11. Okay, let me draw this graph also. Okay, this is how we are drawing the shear force variation and the bending moment variation for this kind of linearly varying distributed load problem. Okay, thank you. See you next time.